we do in 2016 paper. This is Pure Maths Unit 2, right? So let's continue with this particular question. They say given that NPR is equal to n factorial, right, on n minus r factorial, show that 2rpr by npr on 2r factorial is equal to the binomial coefficient NCR. So this is what they're saying to show. Actually, we supposed to know this result, and we also supposed to know NCR, the result for NCR. NCR is n factorial on n minus r factorial by r factorial. So this is actually, they just wanted to show that this thing here would give you this. That's basically what they want us to do, right? So let's show it. Let's get straight into the meat of the matter, right? So we require to show this here, right? That's basically what they're asking us to do. So now let's look at it. Let's show it, right? The first thing I would do is I would rewrite this a bit, right? I would rewrite it. Right, so this is what we have here, right? Or rather, find this and find this, right? So that's basically what I did in the first instance here, using this result here, the NPR, right? So you plug in, instead of n, you plug in 2r, right? So that's how we get 2r factorial, and instead of n here, you plug in 2r as well. So that's how we get this. And then it's just a matter of simplifying, because the 2r minus the r would give you r factorial. So we get this. So that's this first little part there. Then we just put down what that next part is, the NPR. You would get that from here, right? So let's do that next, right? So those are the two parts in the numerator we're looking to work out here. So we just worked out that. And now let's put everything into this big thing and see if we would get this here. So that's what we're doing next, right? So that's what we will do, right? So therefore, this is what they gave us to show that is equal to NCR, right? So what I'm going to do is just rewrite this a little bit differently, right? So this is what I'm going to do here, right? 2NPR, this is the same as, right? Or this on the numerator here is the same as saying 2NPR multiplied by NPR, right? Which could also be multiplied by 1 on 2r factorial, right? So I just rewriting it. And what I'm going to do next is just the thing to complete the question, right? I'm going to substitute what I got for this, which is this here. And then I'm going to substitute what I got for this. Well, that is basically here. That was given from the question. And then see what terms cancel out each other, and see if we get NCR, which we know should be n factorial on n minus r factorial, right? So, yeah, welcome to everybody. Pure Maths Unit 2, just a reminder, that's what we're doing here today. So let's substitute this stuff into it and see what cancels out. So this is what we have, right? We made the substitution, and off the bat, you could see this and this will cancel off each other. You see in the r would come here, right? And you have the n factorial on r, on the n factorial, sorry, on r, on n minus r factorial by r factorial, which is NCR, right? So that just meet, right? Just off the bat, just looking at it as seeing we getting the solution that we need, right? Or that the question is asking us to get, right? So let's just now, all we have to do is just complete it. You see it cancel off there, and then we put everything together, and this we know is NCR. So it's just a matter of saying that is equal to NCR. And what we need to do is just tie up everything, and finally this is it here. We say therefore, right, we have proven what they ask us to prove, and that's it. That is part C, I, right, for part C. So the next thing we have to do is the next question. So that is the first part there, part C, right? And let's look at the second part here now, right? The second part says determine the coefficient of the term in x cubed in the binomial expansion of this here. So you have this binomial expansion, and They want us to find the coefficient of the term in x cubed. So when we think about the coefficient, we could expand it out, right, and find out where's the coefficient, or we could use, if you could recall, there's a condensed formula and a long formula for the binomial theorem, right? So what I'm going to use is the condensed formula, right? So we could represent this function here, this binomial, right? 3x plus 2 to the power of 5 in terms of this here, this condensed formula. And to get the coefficient of x cubed, what we could do is just rearrange the powers right here and make sure that we rearrange it in such a way that we have the powers of x only, right? So you get all the x right together and add their powers. And then what we could do next is try to find the value of r, right? That gives us x cubed, right? And that's basically what we need to do. So this is what we do next. We put it down here, right? And what I did here was basically separated the 3 and the x, right? So I raised the 3 to the power of 5 minus r, and well, I brought it to the constant on the next side and just kind of separated the x so it would be by itself isolated, because I just want to see the power of x. And then all we need to do next is basically equate this to 3, right? Because we remember we want to find the value of r, right? That would give us the term in x cubed, right? Because we want to find the coefficient of x cubed. So that's what we do next. We equate this, the 5 minus 3, right? Or the 5 minus r, sorry, right here, to 3, so that we could find the value of r, right? This is an easy question. You could actually see it off the bat, what r would be, but this is like the process that you would take, right? If it was a higher power, you would use this, this would be more efficient, right? But still, we using this method, and let's go forward, right? So the term in x cubed is given when, right, 5 minus r is equal to 3, so therefore r is 2, right? And all we need to do now is the coefficient of this. If we were to put r as 2 here, we would get x cubed. And then this here would be the coefficient, right? Just that would be the coefficient. So all we need to do to get the coefficient of this term, right, or of the x, of the term x cubed, right, is just basically substitute r is equal to 2 into the coefficient part, which would be this, right? And that's what we do next here. We say therefore the coefficient of the term in x cubed is given by this here, right? And then all you need to do is plug this into your calculator, and you should get 1080, right? That would be the coefficient there of the term in x cubed for this binomial expansion, right? And that's it there. Pretty straightforward, right? Just remember your formula for the binomial theorem. And we have 2 sets of formulas. You have one where the power is positive, a positive integer, right? And then we have a formula for when we have real, right? For any real number, when the power is any real number. So these are the formulas I want to make sure you remember, right? And this is just basically a condensed formula. So yeah, that's it. Let's move swiftly ahead, right, on to the next question. So this is question 4 now. So that was question 3, the little parts in question 3. We completed that. So now we're looking at question 4, part A. The function f is defined as f of x is equal to this here, right? For which this is the domain, right, for x. And then it's saying show that f of x is equal to this. This looks pretty straightforward, right? But we need to show it. So basically, let's put down what is f of x, right? And we require to show this, right? That f of x could be rewritten as this. That's basically what they're asking us to do, to rewrite x in a different form, right? So what I would do is this, right? F of x is the same as the 6th root, right? That function being raised to the power of the 6th root is the same as it being raised to the power of 1 on 6, right? So that's that. Okay, cool. But this function that is showing us, this here is the original function. This is the function they want us to convert it into. This has 3 terms. This has 2 terms. So what I'm thinking here is that this could be factorized. It looked like a quadratic, so factorize it. That's what I would do. So factorize inside here, and let's see if we could reduce this power in some way when we factorize it. So when we factorize it, if you could see it offhand, right? Or if you want, you could do the long way and just factorize it. You would see that this is the same as 2x plus 1 squared, right? So if I were to square 2x plus 1, I would get back this, right? And all we need to do now is rules are indices. Multiply this 1 on 6 by 2, and that would give us the third, right? Which we have up here that they ask us to represent it in terms of, right? So then this is your final thing to do. 2x plus 1 to the power of 1 on 3. And that's it. Pretty straightforward, pretty simple, right? It's just what the question asking you is just to represent this in a different form, right? And the form is this. So that's basically it. And yeah, that's that for that particular question. Let's move on. We almost finished, right? So that's basically it. You say at the end, you just wrap up the question. Hence, f of x is equal to 1 plus 2x to the power of a third, right? Next thing we're looking at is the series expansion for 1 plus k, or rather 1 plus x to the power of k is given by this here. And when I see this expansion here, this expansion that they gave us is actually the expansion for a binomial series where the power, right, is a real number. So this is something that should look really familiar to you all, but they actually give you the formula in this question, which is, yeah, normally they don't do that. You're supposed to know, right, the formula offhand, but they give you the formula, so you use it, right? But let's get into the question now. They say, determine the series expansion of f up to and including the term in x4, right? So we know what f is we backtrack into the question, the previous question part I, right? So we need to recall what that was, right? So that's what we need to do. Recall what f was, right? Recall it was this, remember? And we're using the other form, not the big complex looking form that I had to factorize. Use the other form, right? And basically expanding that using this formula. That's what you need to do. Expand it using that formula. So what we could see easily here is that our k would be a third. Our x would be 2 on x. That's what you need to identify. What is the x and what is the k? Right? And then it's just a simple matter substituting what is the x and the k into this formula that they gave you. Normally they don't give you the formula, right? But they gave you it. So we utilize it. Why not? So we know k and we know what x is. X should be, right, 2x. So what we need to do is just substitute all those 2 values into the formula that was given. And this is what we get in here, right? Remember, it's up to determine x4. So this is what we have. Resuming to the question, this is what we have here now. So what do we do next? That's the question. Well, after making the substitution into the series expansion that was given, right, we just work it out. It's just a matter of now plugging everything into your calculator, right? You could plug this if you want into the calculator. These you plug into your calculator and just, you know, try to find out what are the values there. So when we plug in everything into the calculator, this is what we get. And yeah, that's basically it, you know, because they just say to determine the series expansion of f up to and including determine x4. So after you do that, you just tie it up, right? Therefore, f of x is equal to 1 plus 2, right, on 3x minus 4 on 9x squared plus 40 on 81 x cubed minus 160 on 243x to the power of 4. And that is it. So we stop up to this, determine x4. So you're good to go there. And that's basically it. This one is real simple. There's giveaway marks. There's real giveaway marks for sure, right? So that's that. Next thing, let's move on to the next question quickly. Next question says, hence, approximate f of 0.4 correct to 2 decimal places. So basically, we have to use the expansion that we just found in part 2 to find f of 0.4. So let me do it. First thing I would do is rewrite the expansion, right? That's what we do. Recall that expansion that we got in part 2, right? This is the expansion here. Cool, right? Then all we need to do is to say f of 0.4. So wherever you see x, you put 0.4, 0.4, 0.4, 0.4, 0.4. And then it's just a simple matter of plugging into your calculators and getting the approximate value. This wouldn't be an exact value. This is basically an application of the binomial theorem that is the question is asking you to do. It's asking you to find f of x using the binomial expansion for this function, right? But it wouldn't be the exact value, obviously. It would be an approximate value because remember, we step up to determine x fourth, right? So the next thing is basically to plug it in, right? And I like to just put the little squiggly line there to represent the is an approximate value, right? So we plug in all our values. Wherever you had x, we put 0.4, right? You see in the 0.4, 0.4, 0.4, 0.4, 0.4. So we good to go there. Now, let our calculators do the work. This is where the calculator is a study show, right? You plug it into your calculators, and this is what you get here, right? That is your answer. You can just check it over, make sure, that is the answer that you get. 1.21 correct to 2 decimal places. Remember, that's what the question asked us to put our approximate value to, right? To round it off to 2 decimal places. So that's basically that. That's that part there done. Let's see what else this question has to offer, right? So let's look at part B. So this question for part A we finish. Now we're looking at part B. Part B says the function h of x is equal to x cubed plus x minus 1, right, is defined on the interval 0, 1. Show that h of x is equal to 0 has a root on the interval 0, 1. So that's what we need to do. From the time I see questions like this, and we in module 2, already thinking they want us to show that the root lies within the interval. Just show. They don't want us to find the root. They just want us to show it. So immediately my mind is thinking intermediate value theorem, right? So that's what we need to use, the intermediate value theorem. But first we need to find f of the upper limit and f of the lower limit, or f of the lower limit first and then upper limit. And once there's a sign change, that's what we're looking for. Then by the intermediate value theorem, and since this function is continuous, we could say there exists a root within the interval that the question asked about, right? So I'm talking a lot. Let's actually start to write, right? So we find h of 0. We get -1. Clearly, you could see that. Then h of 1, you get 1. Clearly, we've seen a sign change, so things looking really good. So once we see a sign change, we know that a root lies within this interval 0, 1 for this particular function, for the function in question. What is the function in question? We know the function in question is h of x is equal to x cubed plus x minus 1. The interval is 0, 1. So we're good to go there. Nice. So now, how we tie up this? We'll get some marks for doing this and this, but we won't get the full marks. This is about 3 marks. We need to tie it up by making a statement, right? We need to state that since h of 0 by h of 1 is less than 0, and h of x is continuous, then by the intermediate value theorem, there exists, right? There exists, that's that symbol there, a x is equal to alpha such that f of alpha, right, is equal to 0. This implies that h of 0 has, right? H of x, sorry, is equal to 0 has a root in this interval, right? So that's basically it. That's basically it. That would tie up the question and give you the remaining marks. If you just leave it as this, you'll just get like probably a 1 mark. This would give you a 2 marks, right? The 2 remaining marks, you'll get 3 marks in total for this one. And that's it. This normally an easy question. They will always ask this question in the exam, right? Or most times they ask it, right? So now let's move ahead. It looked like it have a part 2. Part 2 says use the iteration, right, with initial estimate x1. So use this iteration, x subscript n plus 1 is equal to 1 on x squared subscript n plus 1 with initial estimate x1 is equal to 0 to estimate the root of h. So we're still looking at the question previously. I think what they did was they gained the iteration. They used the equation for h to gain this iteration, and that is something as well, right, that they test as well, apart from the normal iterations that we look at, right, which would be like Newton-Raphson, that they actually create an iterative formula from the function h of x. That's how they get this, right? But you don't really have to know, well, you have to know how to do that, but the question not asking you that. They're asking you to use this iteration that they gave you, right, with an initial estimate of x subscript 1 is equal to 0 to estimate the root of h correct to 2 decimal places. So all we need to do here, you have your first estimate, x1 is equal to 0. So all we need to do is find x2 and then find x3 and x4, but we need to know when to stop, right? We will stop when the consecutive terms, the degree of accuracy, when you round them off to the degree of accuracy indicated by the question, which is 2 decimal places, if they give you the same answer, then that is the root, right? Good afternoon, Adrian. So that's basically it. So what we need to do here now is let's find a few approximations and see if any consecutively they will give us the same number when we approximate them to 2 decimal places. Let's look at it, right? So let's write down what we given first. I always like to do that. Any question given, write down what the question gave you. So it gave us the iterative formula here, right? And it gave us the initial approximation or the initial estimate of the root, right? x1 is equal to that. So now what we do is we find x2, right? The second approximation. So we just plug it into the iterative formula. That's it, simple. Plug it into the iterative formula and plug it into a calculator and get the answer. So we'll get this answer here. I normally round off any answer. Since it's 2 decimal places, I would round it off to about 4 decimal places, right? Just to make sure that when I look into round off this, I know I have some breathing space now. And what I like to do as well is in my calculator, I would store the exact value that the calculator gave me. So it might have like 7 zeros the calculator gave me. So if you all know how to store, that would be really beneficial for these questions, right? So next we move ahead, we find x3, because if you look at this and this, if you round it off to 2 decimal places, they're not the same value, right? Or are they? They are. They are, but we wouldn't use that. We wouldn't use that. They are, but we wouldn't use that in this particular instance. No, to 2 decimal places, they won't be, because this would be 1, right? And 1 wouldn't increase that, or that would be 0.67. This here would just be, it will be 0, 0. Yeah, so it wouldn't be the same actually, right? So let's move on to the third approximation. So let's move on to that. Plug in 0.6711 into the iterative formula now, because that is your second approximation you're using to get your third approximation, right? So we get this. So we always check in. If we approximate this to 2 decimal places, we'll get 0.69, right? 0.69. But this approximated to 2 decimal places is 0.67. They aren't the same. So we have to move forward. We have to go and find the 4th approximation now, right? So that's what we need to do. Find the 4th approximation. So let's do that. we would use x3 to find the fourth approximation. So that's what we do next. So we plug in again, right? And this is what we get when we find the fourth approximation, 0.79778. When I look at this, the previous approximation, the two decimal places is 0.69. This here is 0.68, right? They're not the same. So we have to move forward again. We have to find x5. So let's find x5, right? Using 0.778, which is x4, right? We get this for x5. x5 approximated to two decimal places would be 0.69. This though is 0.68. So they're not the same either, right? The consecutive terms need to be approximated. When we approximate the consecutive terms to the degree of accuracy indicated by the question, the degree of accuracy indicated by the question is two decimal places. It's not the same. So we have to move on. We have to go to a sixth approximation. So that's what we do next. Sixth approximation, let's do. So we would use this to gain the sixth approximation. We would use x5, right? So let's do that. x6 would be this here. And you get this. Again, we look at the consecutive terms, correct them to two decimal places and see if they are the same. Are they the same? 0.68 corrected to two decimal places. That's what this would be, right? When I correct it. This here was 0.69. They're not the same, right? These two, not the same. So we have to go again, right? We have to go again. So what will we go to? x7. So we'll use this. Hopefully we get it on x7. I really hoping, right? So let's see what we get. It's looking like this might just be it. This just might be it, right? So when we look at x6, we approximate that to two decimal places. You get 0.68. x7 approximated to two decimal places will be 0.68 as well. So this is correct. We're good to go there. So because the consecutive terms, right, approximated to the degree of accuracy indicated by the question, which is two decimal places, are the same, we can now state safely that 0.68 is for sure, right, the estimate of the root, right, correct to two decimal places. So that's what we do. We make that statement in the end to tie up everything, and we should be good here, right? This is what we say. We say since x6, right, and x7 correct to two decimal places gives 0.68, then the estimate of h correct to two decimal places is this. And that's the thinking behind these type of questions. The degree of accuracy is key, right? And if the degree of accuracy for the consecutive terms gives you the same number, then that's when we know to stop. And that's basically it, yeah? So that's what you need to keep in mind with these type of questions, always looking and comparing to see whether or not they are the same when we round them off to the degree of accuracy indicated by the question, right? Or the amount of decimal places that they ask you to round it off to significant figures if that's the case. That's basically it for that question. Let's move on to the next question. Use two iterations of the Newton-Raphson method with initial estimate x1 is equal to 1 to approximate the root of the equation this in that interval, right? 1, 2, or give your answer correct to three decimal places. The first thing I would do is actually write down the function given. I would differentiate it because the Newton-Raphson formula, it asks us to differentiate. It has a differential of the function in question in it. So that's what I would do first, right? So that's what I will do. Let's do that, right? So let's say given this here, right? We given this function here, we given x1 is equal to 1. We're not given f prime, but I found f prime by differentiating g of x, right? So the next thing I would do is put on what is the Newton-Raphson formula. It is given by this here. This is very key you need to learn off your Newton-Raphson formula. Learn this. This is what you're learning. This will surely come up in the exam, right? They love to bring Newton-Raphson. So then the next thing is to then try to find the approximates, right? And well, it's the 3 decimal places. So it's a similar principle to the first or to the last question we did with the iterative formula. The degree of accuracy, right? We need to compare the consecutive terms, and once they equal, when we round them off to the degree of accuracy of the question, or that the question asked us to give it in, then we know that is the solution and we could stop, right? So that's what we do next. We're saying therefore when n is equal to 1, right? That's the first thing. That will give you x2. That is your first approximation there. So that's what we get. We get when you plug in everything, right? Your x1 is 1. Remember the question gave us that you plug in your x1 here as 1 everywhere, right? And you would end up with this here. So you should be good there. That's it. That's the x2, right? Your second approximation, right? So then we need to find a third approximation, because if we round this off to 3 decimal places and this the 3 is not the same figure, so let me go again. Let's go to x3, right? We would use x2 to find x3, right? So you need to always keep this figure in mind, right? And as I said, store it. If you know how to store in a calculator, that will go a long way as well. So store it into a calculator and use it for further reference or future reference. And by future reference, I mean use it when you're trying to find x3, right? So let's find x3 now. Same formula we're using, but we plugging in x2 wherever we had x1 in the previous one, right? So when n is equal to 2, this is what we have. And you're plugging in the x2s wherever, and you should get this here. Let's compare them. This rounded off to 2 decimal places, or rather 3 decimal places, because it's 3 decimal places, they said, right? Would be what? 3 decimal places, this would be 1.118. This here would be 1.097. Those two aren't the same, so we have to go again, right? We have to go again. Let's go again. We need to find x4 now. So let's find x4. When n is equal to 3, you use x3 and you substitute it. We get x4. So this is it here. Let's compare. This would be 1.097 correct to 3 decimal places, right? When you correct this to 3 decimal places, you get this here. This correct to 3 decimal places would be 1.097 as well. So you're good to go there. That's correct. So we're real good. So in the end, we could say since x3 and x4 approximated to 3 decimal places are the same value, then, right, the root of the equation g of x would be 1.097 correct to 3 decimal places, right? Since x3 and x4, right, correct to 3 decimal places, right, is the same, then the root of g of x is equal to 1.097, right? Or the approximate root, right? Because remember, it's approximation at the end of the day, right? And that is basically it.